All right, sorry about that. There seem to be some network issues here. All right. Can one of you please confirm that I'm audible?
Yes, sir, you're audible.
Thanks. Okay, so all right. So let's suppose that let's consider two cases. Okay, so case one is when I take the entire sequence x1, x2, x3 up to xn, design the best possible prefix-free code for this sequence, for the n-length sequence, uh, and then so I get one particular code word. Sorry, yeah. I get a particular code word, and the expected code word length or the average rate is equal to so I know that the best possible average rate as n tends to infinity is equal to the entropy, right? Now let's say that I did something different. So case two, I use a prefix-free code for n equal to 1. Okay, so I get, and I encode encode the sequence symbol-wise. So I get C K1, C K2, C K3, and so on. So basically, I'm using the extension of the prefix-free code to encode the n-length sequence. Okay, so the total length of the code word sequence, since I'm using a prefix-free code, I can decode the sequence as well, yeah, quite easily. So the overall length is equal to K1 plus K2 plus so on up to Kn. And the rate is equal to K over N, which is K1 by N plus K2 by N, and so on up to Kn by N. Okay, so this is equal to N times the best optimal rate for N equal to 1. Okay. So now if I compare these two, which one do you think will be smaller? So just to repeat, I'm looking at two different ways to encode an n-length sequence. First, I'm going to design the best possible code which minimizes expected length for the entire n-length sequence itself. So among all possible codes for over among all possible codes for xn, I'm going to design a variable length prefix-free code, and I'm going to encode this. And this gives me an average rate, which as n tends to infinity tends to entropy. Okay. Separately, I'm going to design another code for the alphabet size of x. So I'm going to encode symbol-wise, and I'm going to look at the best possible code which lets you encode the sequence symbol-wise. And I'm going to concatenate all the code words. Okay. And this gives me some rate. Let's call it R. Let's call it R1. Okay. Now, what can you say about R1? Is it going to be less than or equal to h of x? Or is it going to be greater than or equal to h of x? Correct. So the rate in case 1 so is going to be less than or equal to the rate in case 2. So this rate R1 is going to be greater than or equal to R opt n. So as you increase, if you look at blocks of larger and larger size and design a code for that, then it is obviously going to it is going to be better. It is going to achieve a smaller rate than what you would get if you encoded it symbol wise. And why is that? Because if you encode symbol wise, then it's a valid encoding scheme. It's a valid prefix free code, even when you look at blocks of length n. And since you're optimizing over all possible codes for n length sequences, R opt n can only be better than R opt 1. Okay, is that clear? Any questions? Any questions? Okay, so basically, if I want to encode, if I want to compress an n length sequence, there are two ways I can do this compression. One way to do this is to design the best possible code for the entire sequence itself. So the distribution is PXN, which is the product distribution since it's IID. Or what I can do is I can design a code for each symbol. I can design a prefix free code for each symbol and then encode it symbol wise. So basically, I'm designing the best code for the entire block. So case 1 is when I'm designing a code for a block of length n. Case 2 is when I'm designing a code for each symbol. So this is block wise encoding, and this is symbol wise encoding, right? In both cases, I'm designing the best possible code that I can, right? So if I do block wise encoding for a block of length n, then I get some rate Rn. If I do symbol wise encoding, then I can get some rate, average rate, which I call R1. So I claim that R1 has to be greater than or equal to Rn. And why is that the case? The reason is that so both are prefix free codes, right? So what is Rn? Rn is the minimum over all possible prefix free codes for xn. For xn, right, of the expected rate, right? So this is our Rn, right? And what is R1? R1 is the minimum overall prefix free codes for x of the expected length, right? Now, if I encode symbol wise and take the concatenation of the code words, then basically I'm going to get another prefix free code, right? So the extension of any prefix free code is always a prefix free code. Right? So so the rate that I can achieve over here, so every extension is also a valid code over here. But then you're minimizing this all possible codes of xn, and one such code is the code that you design for n equal to 1, or the extension of that which you get for n equal to 1. Right? So since you're optimizing over all possible codes, which includes the codes over here, the rate can only be smaller. So Rn can only be less than or equal to R1. Is that clear? So basically, the extension of the codes that you optimize over here are already included in all possible codes over here. So this is a larger class of codes. So the set of all prefix-free codes for xn contains the set of all contains all extensions of prefix-free codes for x1. Okay. So now we've seen that obviously R1 is greater than or equal to Rn. Okay. But then what is the best R1 that we can achieve? Or for any finite n, what is the best possible rate that we can achieve? Right? So let's see what it is that we can achieve. So first we'll try to prove a lower bound on R1. Okay. So we are going to prove, so one way to derive a lower bound is the following. So we want a prefix-free code which obviously imposes a constraint on the code word length. So suppose that I have x, I encode it to a code word ck, right? So this has length k of x, right? So the expected code word length, let me call it L. This is expected value of k of x. Right? But we already know that if it is to be a prefix-free code, then the code word length should satisfy Kraft's inequality. Right? So sum overall x in x of 2 to the minus k of x should be less than or equal to 1. So this is a constraint that we must satisfy, and we know that as long as we have a set of lengths which satisfies this, we can construct a prefix-free code. So if we want to find what is the best possible, what is the minimum expected length, then all we need to do is to solve this optimization problem. So the optimal expected code word length is equal to the minimum of the expected code word length. So it is the minimum sum over all x of p of x, k of x. This is the expected length. And what is the minimization over? The minimization is over all possible k of x which satisfy sum over all x in x 2 to the minus k of x less than or equal to 1. Right? So this is a constrained optimization problem. Now, unfortunately, even though this is a constrained optimization problem, the variables involved are not continuous, they're discrete. Right? Nevertheless, we can look at a relaxation of this optimization problem where each k of x could be treated as a positive real number, and then you can round it off to the nearest integer. So that's one way. You can solve this, you can use Lagrange multipliers or your favorite convex optimization technique, and then solve this optimization problem and you'll get a number. But then there's a more nicer way to do this to get a lower bound. Right? And we'll see that L opt is always greater than or equal to h of x. Right? So far we've seen that we can achieve h of x, right? So in the I guess in the second class or so, I gave you a scheme which achieves h of x asymptotically, but we never saw that it is the best possible achievable rate, right? It's possible that you could potentially achieve a rate even below h of x, but in fact that turns out to be impossible, as we will see next. So for any prefix-free code, the optimal, the best possible, the minimum expected length always has to be greater than or equal to the entropy of the source. Right? And equality is satisfied. So in this particular inequality, this inequality becomes an equality if and only if p of x is equal to 2 to the minus k of x. So the length assigned to a particular code word is equal to log 1 over p of x. And to prove this, we'll use some of the properties we've seen in our information theory or information sciences course. So what we'll do is we look at the difference between L opt and h of x. Okay, so what is this? This is summation overall x of p of x, k of x. So that's the expected length minus sum overall x of p of x log 1 over p of x. Right? All right. Now what I'm going to do is I'll write this k of x as log of 2 to the minus k of x. So this is summation x in x p of x log 2 to the k of x. Okay, so then this becomes p of x log 2 to the k of x minus p of x log 1 over p of x. I can take the p of x outside, so I'll get log 1 over p of x. Right? So this is summation overall x p of x minus log I want to write it in a slightly different way. So it is log 1 over 2 to the minus k of x. Right? So 2 to the k of x is equal to 1 over 2 to the minus k of x. This minus log 1 over P of x. This is P of x log P of x divided by 2 to the minus k of x. Right? So far I've done nothing much. I've just taken lopt minus h of x, and I've just done some basic manipulations involving the log and 2 to the something and so on. Right? These are just basic manipulations. So does this expression look familiar to any of you?
Tail divergence.
Yeah, it looks similar to the Kale divergence, although this is not exactly a Kale divergence. Can you tell me why this is not a Kale divergence? Yes. So the expression looks like a Kale divergence, of course. It's exactly identical, but I can't claim that this is a Kale divergence exactly as Kusumapriya points out. 2 to the minus k of x is not a valid PMF. All we know is that since it satisfies Kraft's inequality, summation over all x 2 to the minus k of x is only less than or equal to 1. It's not equal to 1. So it's not necessarily a valid PMF. Right? Okay, so therefore, but what I can do is, we know the log sum inequality. This is exactly in the form of where we can use the log sum inequality, and this is greater than or equal to sum over all x p of x log summation over x p of x divided by summation over x 2 to the minus k of x. Right? So 2 to the minus k of x is less than or equal to 1, or 1 over 2 to the minus k of x. So this term in the denominator is less than or equal to 1. So 1 over this is greater than or equal to 1. Right? 1 over some 2 to the minus k of x is greater than or equal to 1. So this entire term, so summation p of x is 1 log, again the numerator is 1 divided by something, but this is less than or equal to 1, so it's greater than or equal to 1 log 1 over 1, which is equal to 0. Right? So L opt minus h of x is greater than or equal to 0, or L opt is greater than or equal to h of x. Right? So let's quickly go through this once again. So we started off with the minimum expected length minus h of x. I did some manipulations to bring it to the following log sum form. Right? And then I just applied the log sum inequality, and I made use of the fact that this is a prefix free code. So summation 2 to sum over all x 2 to the minus k of x is less than or equal to 1, and that just gave me the following term 1 log 1 over 1, which is equal to 0. Right? So the minimum expected length always has to be greater than or equal to h of x. So in general, if I'm designing a code for blocks of length n, then L opt is greater than, always has to be greater than or equal to h of xn, since I'm designing codes over blocks of size n, and therefore R opt always has to be greater than or equal to h of xn by n. So as long as I'm trying to design a prefix-free code, the expected rate always has to be greater than or equal to h of xn by n. This is a strong lower bound. I can't really do any better than h of xn by n. So in fact, the code that we saw in the second class was almost optimal. So almost optimal because there was a small overhead because we had to store the header which took order log n bits. So as long as you ignore that order log n bits, it was in fact optimal. You can't really do any better than that. Okay, so any questions?
So can you give an example of designing a code for entire block?
Or designing for an entire block. So okay, so we'll see that in maybe 5 minutes or so. Just hold on to that thought. We'll in fact see how to. Of course, we can't really guarantee that we will achieve entropy, but then we'll get close to the entropy. So, so okay. So maybe a quick example of the difference is, let us say that the alphabet has three symbols, A, B, C, right? Uh, so if I design a symbol wise code, then maybe A is assigned 0, B is assigned 1 0, C is assigned 1 1. So these are the code words corresponding to A, B, and C. And now if I want to encode, and if I encode symbol wise, then A will be assigned the code word 0 0, AB will be assigned the code word 0 1 0, AC will be assigned 0 1 1, BA will be assigned 1 0 0, and so on. This is if I do symbol wise encoding. Right? So this is symbol wise encoding. Now I can design a separate code for uh, for the alphabet size of x square. So x square. Right? So I look at AA, AB, AC, BA, BB, BC, CA, CB, CC, right? Maybe so. This is one possible code. I'm not claiming that this is good or anything, but 0, 1 0, 1 1 0, 1 1 1 0, 1 1 1 1 0, and so on. Right? So all the way up to what? 1 1 1 1 1 1 1. Okay, this is one code. If I design block wise, note that this is not symbol wise encoding, right? And this is what I would get if I use the extension of the symbol wise encoding scheme. Okay, any questions? Okay, so maybe this is a good time for a quick quiz. Here is I put the link in the chat box. Okay, so you can take maybe 1 more minute. Is there anyone who hasn't submitted the quiz yet? Anyone yet to submit the quiz? Okay, so I'll stop accepting responses. Okay, so let's continue. Yeah, so before we proceed, there was one last part that was left out. So in this particular uh, derivation, the only place where we used an inequality, where we got an inequality, was this point. Right? So this is greater than or equal to this, and of course this point. So these two were the only places where we had strict inequalities. Everywhere else, these were all equalities, right? So when is L-opt? So L-opt will be equal to h of x if both of these are equalities. And when can that happen? So we use the log sum inequality and the fact that 2 to the minus k of x is less than or equal to 1. So we have equalities in both of these places only if the log sum inequality is an equality and 2 to the minus k of x is a valid PMF. Right? So when does that happen? When do you have equality in the log sum inequality? Anyone? Yes?
If AI by BI equals constant.
Correct. So if AI by BI is a constant, and in this particular case, it can happen only if AI is equal to BI, right? Because both of them are valid PMFs. So P of x divided by 2 to the minus k of x should be equal to a constant, or equivalently 2 to the minus k of x is equal to P of x divided by alpha. Since P of x is a PMF, if you sum both sides over all possible x, then you get summation over all x 2 to the minus k of x is 1 over alpha. Right? So you have equality here if 2 to the summation 2 to the minus k of x equal to 1 over alpha, and 2 to the minus k of x is equal to p of x over alpha. And you have equality in this particular step only if 2 to summation 2 to the minus k of x is equal to 1. So alpha should be equal to 1, and therefore in both these steps, if you combine these two, you have equality if and only if 2 to the minus k of x is equal to p of x. All right. So, okay, so now we've seen a lower bound on the minimum possible expected length, and we know how to design prefix-free codes using Craft's inequality. But we still haven't seen any technique to design an optimal prefix-free code or a close to optimal prefix-free code. Let's do that. So the
Sir,
first code we, yes,
I
yes,
have a
Anand.
doubt, sir.
Yes, please.
Sir, in like what cases k 2 power minus k of x is going to be a proper PMF, sir? What values
So,
for k of x?
so one example is the following. So if I take k of a to be say 1, k of b to be 2, k of c to be equal to 2. Okay, so so 2 to the minus k of a is half, 2 to the minus k of b is 1/4, and 2 to the minus k of c is 1/4. So this is a valid PMF, right? So this is one example, right? And if indeed p of a is equal to half, p of b equal to half, and p of c is also, sorry, p of b is 1/4 and p of c is also equal to 1/4, then we'll in fact have equality in the above statement.
Sir, like how do we achieve generalization over it, sir? Suppose if I have 100 bits, like how do we decide then?
So in
In
general, it's not possible, right? So if I give you a code, then you can say whether it satisfies Craft's inequality with equality or not, right? But in general, I mean, it may not be always possible to design a code where 2 to the minus k of x forms a valid PMF. The only statement that we're making here is that if it is a valid PMF, then you have equality. Otherwise, it is a strict inequality. That is all.
okay, sir.
Right? So it may not be always possible. So for every given PMF, it may not be possible to achieve this with equality.
Okay, sir. Thank you, sir.
Yep. Any other questions?
Sir, I have a doubt in the quiz question.
Okay.
Sir, in second question, it is written, consider a code with code word length 1 to 2. Does there exist a prefix-free code with this code word length?
Correct.
Sir, it can be or it cannot be. Like if you take 0, 0, 1 and 1, 0, then it
Okay.
is not a prefix-free code, sir.
Correct. So the question was, does there exist a prefix-free code, right? There exists at least one prefix-free code, and that is 0, 1, 0, and 1, 1. So this is a prefix-free code.
Yes, sir, but it will not means occur all the time, right, sir? Because sometimes it may not be also.
Yeah, but there is one prefix-free code, right?
Yes, sir.
So the question is, does there exist a prefix-free code? And there exists a prefix-free code, right?
Okay.
Okay, so now that we've seen one particular, so now that we've seen a lower bound on the minimum expected length, let us see a construction which lets us get close to entropy. Okay, so the first thing that we'll do, so we've seen that if if our code is supposed to be, so if you want to achieve a rate close to the entropy, then then optimality is achieved if 2 to the minus k of x is equal to p of x. Right? It's not always possible to achieve this. Right? So if 2 to the minus k of x is equal to p of x for all x, then we have equality over there. So then we can achieve an expected length of equal to entropy. So this is the same as saying that k of x is 2 to the minus is log 1 over p of x, right? So this statement here above, so this condition can occur only if p of x is always 2 to the minus some constant for, so, or 2 to the minus some integer for all x. Right? So such PMFs are called dyadic. So we can achieve entropy only if we have a dyadic PMF. If it is not a dyadic PMF, then it is impossible to achieve entropy. Right? So if it is a dyadic PMF, then k of x, so log 1 over p of x, is a valid PMF, and then we may not have a problem. But in general, log 1 over p of x may not be an integer. So what do we do? Let us just select a code word length. So my goal now is to design a prefix-free code. And I'll design the prefix-free code by first fixing the code word length. So I'll take k of x to be the ceiling of log 1 over p of x. Okay. So this is one choice, right? I'm just going to choose k of x to be log 1 over p of x. Now, if I choose it this way, let me first check if the corresponding code word lengths satisfy Kraft's inequality. So 2 to the minus k of x summation over all x. So what is this equal to? This is summation over all x, 2 to the minus log 1 over p of x. So it is the ceil of this, and this is, what can we say about this? So this is ceil log p of x, but this is less than or equal to log minus log p of x plus 1. Right? So this is going to be less than or equal to summation over all x 2 to the log p of x. So this is log 1 over p of x is less than or equal to log p of x plus 1, but is always greater than or equal to log 1 over p of x. Right? So ceiling of log p of x, log 1 over p of x, is greater than or equal to log 1 over p of x, and it's less than or equal to log 1 over p of x plus 1. So minus log 1 over p of x is going to be is going to be less than or equal to minus log 1 over p of x. Log 1 over p of x. So this is summation over all x 2 to the log p of x, which is summation over all x p of x, which is less than or equal to 1. So this satisfies Kraft's inequality, and therefore I can construct, so the code word lengths k of x equal to ceil log 1 over p of x. This satisfies Kraft's inequality, and therefore it is possible to construct a prefix-free code with these lengths, right? And what is the rate that we can achieve, or what is the minimum, what is the expected length that corresponds to this particular code? So this is the expected value of ceil of log 1 over p of x. This is expected, this is less than or equal to expected log 1 over p of x plus 1, which is entropy plus 1. So now we have we know how to design a prefix-free code which achieves an expected length which is at most 1 bit away from the entropy, right? So we'll see an example of this in the next class. Any questions? Yeah, any questions?
Excuse me, sir. Sir, I registered this course like recently, sir. So I didn't
Huh?
get any mail.
Sure, sure.
Yes.
So I'll anyway send a broadcast email to everyone with the links to both Piazza and Google Classroom.
Okay, sir. Sir, like, will they? I mean, I mean, the previous quizzes, like which I haven't, I mean, written. I mean,
Sure.
previous with sorry, sir.
Yeah, sure. I can, if you joined late, then I can give you a makeup quiz.
Yes, sir. Thank you, sir.
Okay, so if there are no further questions, then we'll end this meeting.